Welcome to Module 2. In Module 1, we built a mental model of Ethereum as a global computer. We learned that transactions trigger state changes. But now we need to understand how that actually works. What's happening under the hood when you call a smart contract? How does the network stay synchronized? And why does every operation cost a specific amount of gas? That's what this module is about. We're going to understand the EVM on a deeper level. Let's dive in. In Module 1, I said Ethereum is a world computer and the EVM is its CPU. Let's expand on that. The EVM is literally the CPU, the processor that executes every instruction in every smart contract. But here's what makes it radically different from your laptop CPU. There isn't just one EVM, there are thousands of them running in parallel around the world. Each one executes the same bytecode, processes the exact same transaction, and produces the exact same result. Thousands of independent computers arrive at identical answers without any central authority telling them what the answer should be. Ethereum is fundamentally a state transition system. Think of it like a mathematical equation. New state is equal to the state transition function applied to current state plus a transaction. That state transition function, that's the EVM. Every node in the network runs this exact computation. That's why Ethereum remains consistent. That's how distributed consensus works. So why should Ethereum be deterministic? Well, determinism means the same input, same code, and same output every single time on every single machine. Imagine 10,000 identical calculators. You punch in 2 plus 2, they all return 4. If even one returns 5, it's broken. That's rejected. Ethereum works in the same way. The EVM must be deterministic or the system fails. When a transaction comes in, node A runs it and gets result X. Node B runs it and gets result X. Node C runs it and gets result X as well. They all agree. Consensus happens naturally, without negotiation, because they all computed the same thing. Determinism, however, does have a few constraints. Smart contracts cannot call APIs, they cannot access the internet, they cannot use the system clock, they cannot generate truly random numbers, and they cannot access any external data. Why? Because if one node had internet access and another didn't, they'd compute different results. The system would fracture. If one node's clock was different from another's, time-dependent code would diverge. If randomness was truly random, every node would generate different random numbers, and they'd never agree. External data is the enemy of determinism. That's why Ethereum has oracles, separate systems that bring external data onto the blockchain in a controlled, deterministic way. But the EVM itself, pure deterministic computation. The EVM has a very specific architecture. It uses 3 different types of storage, and understanding the difference is critical. First, we have the stack. Picture a stack of plates. You can put the plate on top. You can take the plate off the top, but you can't pull one in the middle. That would crash the whole stack. The EVM stack works exactly like this. It's what they call LIFO, last in, first out. The maximum depth is 1024 items. Each item is a 256-bit word. That's 32 bytes of data. Most EVM operations work by popping values off the stack and pushing results back on. It's fast and simple. Second, we have memory. Memory is like a whiteboard. During execution, you can write on it, read from it, and erase it. But when the function finishes execution, the whiteboard is erased. Memory is temporary. It's reset after every transaction or function call. Memory is also cheaper than storage. Writing to memory costs far less gas than writing to storage. Memory is used for function arguments, intermediate calculations, and building return values. Third, and most important, is storage. Storage is a permanent filing cabinet. Anything you write there stays there forever. Storage is on-chain. It's part of Ethereum's global state. Every storage value is replicated across every node. Storage is organized into 32-byte slots. Slot 0, slot 1, slot 2, and so on. Storage writes are expensive, extremely expensive. Writing a new value to storage costs roughly 20,000 gas. Reading it costs 100 gas. That's a 200 times difference. Most gas optimization revolves around one thing, that's reducing storage rates. So to recap, the stack is fast and temporary. Memory is cheaper than storage and temporary. Storage is permanent, on-chain, and expensive. Choose wisely when you write your smart contracts. Let's zoom in on the stack, because understanding it is crucial to understanding how the EVM actually executes code. The stack is a last in, first out data structure. It's got a maximum of 1024 items deep. It's got a maximum depth of 1024 items. Each item is a 256-bit word. Look at this simple example. The first operation we have is a push 2. This pushes the number 2 onto the stack. The stack now has one item, that's the number 2. The next operation is push 3. This pushes 3 onto the stack. The stack now looks like 2 and 3, with 3 on top. The next operation is add. This pops the 2 values off the stack, the 3 and the 2, it adds them and then pushes the result. The stack now has the result of 5. Why would we use a stack, you might wonder? Why not just a regular list? Well, first, it's simple and fast. Stack operations are incredibly efficient. Second, it's a natural fit for the instruction set. Almost all operations are stack-based. Pop operands, compute, push result. When you compile Solidity code down to bytecode, it becomes a sequence of these stack operations. Memory is different from the stack. It's more flexible. Memory is a temporary whiteboard. During execution, you can read from it, write to it, and erase it. You can theoretically use as much memory as you want, though memory expansion costs gas. Memory is not part of the global state. When a transaction finishes, memory is discarded. Each transaction or function call starts with a fresh, empty memory. No data carries over from one call to the next. Memory is commonly used for storing function arguments, intermediate calculations, building return types, and temporary arrays. Writing to memory costs far less gas than writing to storage. Now storage. This is where the real cost comes in. Storage is a persistent filing cabinet. Anything you write here lives on-chain forever. Storage is part of Ethereum's global state. Every piece of data stored here is replicated across every single node in the network. Every node must store your data, and that's expensive. Storage is organized in 32-byte slots. Slot 0, slot 1, slot 2, and so on. In Solidity, when you declare state variables that automatically map to slots. For example, if you declare a contract that has a state variable UN256 public count, and the next one address owner, count goes into slot 0 and owner goes into slot 1. There's one more type of data to understand, and that's called call data. Call data is the input data passed into a function. It's read-only. You can read from it, but you can't modify it. Call data is cheaper to read than memory. That's why external functions prefer to take arguments via call data rather than copying them into memory. Call data has a standard structure. The first 4 bytes are the function selector, a unique identifier for the function which you're calling. The remaining bytes are the encoded arguments, the data you're passing to that function. For example, if you have a function that is transfer with the arguments amount and to, the call data would contain the transfers function selector, the to address, and the amount value. Call data is important for gas efficiency. When you read from call data, instead of copying data into memory, you save gas. This is another optimization pattern that skilled smart contract developers use. Now, let's look at various gas costs for different operations. A simple arithmetic operation like add, that's 3 gas. Reading from storage, which is an S load, more expensive, about 100 gas. Writing to storage, that's an S store, much more expensive, about 20,000 gas. The pattern is clear. Storage operations are the most expensive. This is deliberate. The EVM charges high prices for storage to prevent bloat. If storage were cheap, everyone would store everything on chain and the blockchain would become gigantic. By making storage expensive, the protocol incentivizes developers to use it only when necessary. Most gas optimization focuses on reducing storage operations. We've talked about gas per operation. Now let's talk about the bigger picture, gas limits. The current block gas limit is about 60 million gas. This means all transactions included in a single block cannot exceed 60 million gas total. This is a hard cap set by the Ethereum protocol. It prevents blocks from becoming infinitely large. When you send a transaction, you set a transaction gas limit. You're saying, I estimate that this transaction will use up to X gas. If it uses more, stop and revert. A typical transfer uses about 21,000 gas. A complex smart contract call might use 100,000 or more. If your transaction hits the gas limit, execution stops immediately. All state reverts and changes are undone. Gas limits protect the network against infinite loops, DOS attacks, and excessive computation. Now let's trace exactly what happens when a transaction comes in and modifies state. I'm going to use a real example, calling the increment function on a counter contract. Step 1. First, the user sends a transaction to the counter contract, calling the increment function. The transaction includes the contract address, the function to call, the caller's signature, and a gas limit. Validators receive this transaction and validate it. Is the signature genuine? Does the sender have enough ETH to pay for the gas? And is the nonce correct? A nonce is something that prevents replay attacks. It's otherwise known as a number only used once. If any of these checks fail, the transaction is rejected. But in this case, they all pass. The validator's EVM loads the current state, the counter contract's bytecode, the current value of count from the storage, an empty memory space, and it initializes the gas counter. Now the EVM executes the smart contract bytecode step by step. The increment function does count plus equal 1. In other words, adds 1 to the current count. At the bytecode level, this is several operations. If execution succeeds without running out of gas, the new storage value is committed, the transaction is finalized, gas is deducted from the sender's account. If the execution fails, maybe there's a required check, or gas is run out, all state changes revert, the transaction is rolled back as if it never happened, but the gas is not refunded. The sender still loses it. This is crucial. Failed transactions still consume gas. You pay for the computation attempt, whether it succeeds or fails. There's an important property of Ethereum transactions called atomicity. Atomic means all or nothing. Atomicity means all changes succeed and are saved, or the entire transaction reverts and nothing is saved. There is no in between. There's no partial success. Imagine a smart contract with a require statement that requires the amount to be less than the balance of the sender. If the require check fails, the user doesn't have enough balance, the entire transaction reverts. The balance isn't decreased, the ETH isn't sent, it's as if nothing has happened. But the gas is still consumed, the user still pays for the failed transaction. Atomicity is crucial for smart contract correctness. It prevents partial updates that could leave the contract in an inconsistent state. As a developer, you don't have to worry about what if the transfer fails halfway through. It won't. Either the whole thing succeeds or the whole thing rolls back. That simplifies smart contract logic enormously. Let's recap. The EVM is a deterministic virtual machine. Same input, same code, same output. Always. Thousands of nodes compute identically across the globe. Consensus emerges naturally from this shared computation. The EVM uses a stack-based architecture with a maximum of 1024 items. Data is organized into memory and storage. Memory is erased after execution and is cheap. Storage is permanent and is expensive. Gas is charged per opcode, preventing abuse and incentivizing efficiency. Transactions are state transition triggers. They tell the EVM what computation to perform. Execution is atomic. It's all or nothing. Either the entire transaction succeeds or it all reverts. Ethereum security comes from determinism, not trust. Every node independently verifies that the rules were followed. They compute the same thing and arrive at the same answer. No central authority is needed and no trust is required. Just mathematics and incentives. In Module 3, we'll build on this understanding and learn how to write smart contracts that run on this engine.